Jonathan, are you ready to start?
Yep, yep. Let me just get that one up and running. Got it. Okay, can you see that one?
Yeah, go ahead.
Great. Thank you very much, Fumia and Josie and the other organizers for putting this together. It's been great 2 days, and it's going to be a great extra couple of days, I think, on top. Today, I would like to talk a little bit about some of the work we've done in the soft robotics group in Bristol University, where I lead the soft robotics group in Bristol Robotics Laboratory. And I really want to focus today on some work that we've done on working towards artificial organisms. So I view robots really as a stepping stone towards this thing. I think Barbara mentioned it, and Stoyan was touching on this area of a larger number of smaller, simpler organism-based entities and autonomous systems rather than robots. So I suppose one thing I should do in this conference is to, I'll give you a little bit of context. So I think why organisms? Well, there are, oh, I think I might be on automatic pilot at the moment. There are about 30 trillion cells, human cells in the human body, but we have more bacteria in our bodies than we have human cells. So these organisms are ubiquitous, but they go from about half a micron for the smallest bacteria up to what, 30 meters for the blue whale. These are big things and they cover huge ranges. Now, if we can trap that and we can use those concepts in our robots, then we've got the ability to have very, very sophisticated and very functional. So I suppose in this context, I ought to declare what I think about embodied intelligence. And I really don't like definitions per se. And I think really I go to the simplest case. And the simplest case is that you can view an organism as having a brain and a body. And typically we would separate those in our robot like this, and we'd have some kind of linkage between the two. But of course, more and more we discover that this kind of embodied intelligence is more functional, more useful, and it's what is used in nature. But I do like to draw a graph like this. And a graph like this says we've got two axes. One is control complexity and one is morphological complexity. And you can plot things on that graph. You can plot organisms on there. You can plot robots on there. You can plot humans on there. Why not? So here we've got something very simple, like a robot arm, which actually, in terms of control complexity, maybe is quite complex. You have to have interesting kinematics there. Let's just call it complex. And yet the morphology is incredibly simple, right? It's just a couple of metal beams or plastic beams and some encoders and some motors. And at the other end, we have a very simple control system, or at least ostensibly simple, right? I mean, you think that the octopus is controlling this with very simple instructions from its brain. But actually the morphology is taking over. Okay, so our goal really as roboticists is to turn this kind of robot arm here and move up with the function, keeping the functionality up to this kind of complexity where we have less of a requirement for control. Okay, so I think we all buy into that. But the one thing that I would say is it's not easy to do that. So we need to get there. And one of the stepping stones is really to look at smart materials and smart structures. Now, I can explicitly say that because that's an area that we work in, and I'm going to touch upon some of those in a second. But if we do that, we bring smart materials into these artificial organisms, we can make them lower cost, we can make them larger numbers. Ubiquitous is a word that I like to use. These robots are going to be everywhere, environmentally friendly, biodegradable, edible, and as one of my researchers says, delicious. I'd like to have delicious robots too. But in terms of the numbers, we think of robots in hundreds and thousands, and at the moment in the world, we make a few million every year. But I'm talking about numbers which are way up there. I'm talking about billions, trillions, even up to Avogadro's number here, molar numbers, I call them. Well, that's a little bit misleading. So we've done a lot of work in this field by trying to understand what an organism does and then how we could replicate that. So one example, and others have looked at these too, are euglenoids, microorganisms that swim in relatively high Reynolds numbers, and they've got kind of ability to bend and twist. So we've replicated those from a functional point of view as this kind of soft pneumatic robot, or in this case, a hydraulic robot. So that works, okay? We could kind of get the functionality from it, but there's one thing we're missing, and that's what's happening in the structure of the organism. And if you start looking at what's happening on the skin of the organism, it's not using muscles inside the body to bend and twist itself. It's using deformation across the skin. So it has these pellicle structures with motor proteins and motor functions here. So touching on what Stoyan was saying earlier. And with that, the organism can bend and twist into a whole variety of different shapes. So we can replicate that with smart systems which have got actuators embedded into pellicle structures on the skin. And that gives us another route into kind of smart organism-like behavior. We took the kind of smart materials end a little bit further by looking at organelles like the cilia. So here's a cilia from Chlamydomonas volvox. It's doing an awful lot of really interesting organized behavior. And we've tried to replicate that with a smart material. In this case, it's an ionic actuator with 3 segments, and we give it 3 distinct control signals. And it does a pretty good job, considering that the large number of degrees of freedom in the original system have been replicated by 3 inputs. And of course, it does that because of the adaptability of the materials, and also the interaction of the materials with the environment. So that gives us extra hints as to how we can embed within our smart materials and within the structures a kind of a correlation to get some intelligence into the structure. And I don't think those can be ever removed. You can't take one and remove it from the other. So more recently, we've been trying to study more about the skin organism on cephalopods and other organs or other animals. And one thing that the cephalopod does is have skins with embedded muscles. And we've taken that concept and we have built this, which is the electroskin robot. Electroskin robot has got actuation built in, it's got sensing built in, and it's got gripping built in. And those 3 are not independent. We can't have actuation without the sensing being affected. We can't have the gripping without the gripping being affected by the actuation. So in this case here, we take the robot, it's all scrunched up in a pocket, and we take it out and we stretch it and we throw it on the table, and it crawls across the table, exploiting that combination of sensing, actuation, and gripping. And of course, you could flip it upside down and you could move a rubber duck. You know, there's lots of interesting things with you can do with these kind of morphological actuation sensing control systems. And then you wrap it up and you stick it back in your pocket. So very convenient. Now, these behaviors have got very interesting properties, which mostly we don't like, at least from an engineering point of view. And they're highly nonlinear. So if you take this actuator on the top left here, when you actuate it, it squeezes and then it goes out of plane, which is really annoying. But you can harness that instability and you can do things like replicate the passing cloud and the other patterns that appear on the sides of cuttlefish. And if I show you some of these simulations, and the simulations here show that we can generate the patterns using these materials that generate the passing cloud, these kind of quasi-static immersion patterns, but also my favorite, this one down here, which produces effect of just a random pattern. Now, the ability to generate a kind of random chaotic pattern, I think, although it's not seen in nature, these materials generate those patterns. So perhaps we can go beyond the natural organism to generate something which is, really different and useful for our artificial applications. So we've done some work to extend our materials domain into hydrogels, and this is some work that's going to appear soon on self-heating, edible, biodegradable, functional gels, and it will self-heal in water, which is a really nice new capability. We've also been looking at different kinds of actuation mechanisms, and in this case, we've done some work on electrostatic actuation. We have a whole family of new actuators which are existing in this area, and they can be used for actuation, for sensing, for energy harvesting, and for generating basically arbitrary shaped or origami type structures. And my favorite is the one at the bottom left here, where we can make a complete actuator artificial muscle from a piece of paper and a pencil. You just write on your electrodes, you dip it in oil, you apply your voltage, and then it contracts. And that, to me, is a really good route into making very simple organisms, very simple structures, which have got the kind of interesting abilities that we want. And on the right is some new work that was published last month on packaging that up to turn it into actuators which will replace conventional electromagnetic pumps in, for example, wearables. Of course, that's embedded intelligence through the materials, but we can be just a little bit more explicit by taking conventional control and turning it into something with the materials that we've used. Why? Because if we're going to make that artificial organism, we don't want to put the silicon chips in there. We don't want to put the conventional materials in there because they're not scalable in terms of cost or size or degradability. So instead, we've been developing what we call the soft matter computer. And the soft matter computer is a fluidic electrosystem. And by having a program of fluids driving around a circuit, which is encoding a program, and receptors, which will interpret that program, we can generate arbitrary logic gates and combinations of those logic gates, therefore to generate almost any computational system in the digital world, but also these structures will undertake some very complex filtering. So we've got analog computation as well. So the ability to do that is quite nice because this system, not only is it embedded, but also it's affected by the body. So the computation in this soft system is affected by the deformation of the robot or the organism. So you've got that close coupling then of the body and the computation. And it really is a kind of a very explicit link between embodiment and intelligence in this case, thinking that the computation system will change when the robot changes its environment. Why? Because its body has had to adapt, its computational system adapts, and the two work together. And there's a robot at the bottom showing here the kind of typical fluidic movement. It's sped up. It takes a long time, this particular robot, but you'll see that that's, clearly has got a non-silicon computation system inside. Extending that, we've got a couple of new papers coming up in this area. One on liquid metal being used as this kind of control system, another being linking the bistable structures that were developed in Harvard with Marcus Nemitz with our kind of computational system. So there we've got something which means that previously that system could only control pneumatics, and now we can control almost any actuator. So I think in summary, I'd say, I asked this question at the beginning, can embodied intelligence help us to make better soft robotics? Yes, it can, provided we use these kind of advanced soft materials and this kind of notion of smart structures as well. Thank you very much.
All right, thank you, Jonathan. This is a very good overview of all the work you've been doing.